Today I want to talk some more about spin, angular momentum, and Planck's constant. Starting out by saying proton spin is not 1/2 h bar. And in physics speak, they'll often say a half and just assume the h bar. And so they have this convoluted scheme where all particles are plus or minus a half, or sometimes multiples of a half, and that they add and subtract spins in order to make sure there's an equal number of spins on one side and the other side so they conserve angular momentum. Well, the problem with that is that the proton does not have a spin equal to 1/2, and which I'll talk about. So, spin, because of this issue, is thought to be intrinsic. And you have to remember, as a physicist, intrinsic means magic. It means fairy dust or something, or elves, or manufacturing protons and sprinkling it. Because in abdication of responsibility, physicists are responsible to physically explaining why protons have the angular momentum they do. And if you say they're intrinsic, you're just throwing up your hands and saying, I don't know, but pretending that you do know by calling it intrinsic, which is nonsense. It's not a rational approach to physics to say that anything's intrinsic. You want to understand where it comes from. And once you understand where it comes from, you have to deal with it. So the magnetic moment generally follows the equation here that mu, which is a symbol for magnetic moment, is equal to G, the G factor, times mu sub n, which is the nuclear magneton, divided by h bar times I. And then, in order to keep up with this convoluted scheme, they define I to equals 1/2 h bar. So then mu equals G times the nuclear magneton divided by 2. And so then we can look at the nuclear magneton. There. And that equals the electric charge E times h bar divided by 2 times the proton mass, 2mp. And that sounds innocent enough, except that mass doesn't cause magnetism. Magnetism is determined by the charge, the radius, and the angular velocity. It's not determined by the mass. So what's going on? What's going on is the proton Compton wavelength. The proton has a Compton wavelength that's symbolized lambda p here, and it equals h over c times the mass of the proton. So you can rearrange that and substitute that into the magnetic moment equation to find out what we're really doing when we measure the nuclear magneton, and you end up with it being equal to E, the charge, times c, the speed of light, times the proton's Compton wavelength divided by 4 pi. And that means that mu, the proton's magnetic moment, is G, you put in the G factor, and then that's E times C times the proton Compton wavelength divided by 8 pi. You have an extra factor of 2 in there. So we have a case where the proton Compton wavelength, though, lambda p over 2, which would give us the effective radius, is 0.6607 femtometers. Femtometer is 10 to the minus 15 meters. So that's on the scale of the proton radius, but it's not the proton radius. The current measured value is 2018 of the charge radius is 0.8414 femtometers. And the most recent average is slightly lower than that. So the actual charge radius is different from the proton Compton wavelength, which is what they're assuming in the equation, which tells us the equation's wrong. You're not measuring what's real. You're measuring some fictitious wavelength, or saying that a proton has some fictitious wavelength that it doesn't have. And that ties back to the angular momentum. So, in reality, we have the magnetic moment being g, the g factor, times e, the speed of light, and c, the speed of light, times the charge radius, r sub p, divided by 4 pi. And that gives you the real magnetic moment of the proton. At least real enough until we define exactly what the charge radius is and what g needs to be, because those two things can vary in a dependent way so that the magnetic moment is the same. So next we can look at angular momentum. Well, angular momentum classically is the mass. How much mass do you have? What's the radius? And how fast is it rotating? So that's why I started out with magnetic moment, because that explains the problem. Then we can go to magnetic moment and angular momentum, and then we can see how it has the same problem. So we start out with the mass times the speed of light times the charge radius divided by 2 pi, because the angular velocity is c divided by 2 pi. But once again, you can substitute in the proton's Compton wavelength, and you get h bar times the charge radius divided by the proton's Compton wavelength. And that's what the angular momentum is, physically, if you go by the charge radius instead of this fictitious radius of half the proton Compton wavelength. And so if you calculate the ratio of the charge radius divided by the Compton wavelength, you get a factor of 0.6367 h bar. And 0.6367 h bar does not equal half h bar. So that proves my point. Proton spin is not a half. It's greater than a half. And so the assumptions that electrons and protons have the same spin is false. If you go through the same exercise with electrons, it does turn out to be 1/2 h bar. And you have to use the Compton wavelength, which is significantly larger, 2.42 times 10 to the minus 12 meters. So the effective radius of the electron is larger. And like the proton, we know the proton shell is, or we suspect the proton shell is made of quantum fluctuations because it's not made of anything else. And similarly, if you have a Compton wavelength sized electron shell, it too must be made of Compton quantum fluctuations, or else it would be more observable. So we also have the problem that neutrons don't have spin 1/2 either, because the neutron doesn't have the same mass of the proton, so it doesn't have the same effect on the nuclear magneton. And even if it did, its Compton wavelength is not the same as the proton Compton wavelength. And also, its true radius is not the same as the true radius of the proton. So the neutron's actual angular momentum is probably close to that of the angular momentum of the proton, 0.65, but not 0.65, maybe a little bit more. We really don't know, because we haven't really nailed down what the radius of the neutron is. We just know that it has to be similar to the proton. And so we have a case where the electron, proton, and neutron all have different angular momentum. So as I said at the beginning, this entire scheme where all the angular momenta of all the particles add up, and you can set up equations and you can add up the spin on one side and the spin on the other side so that the angular momenta equal, and that's all contrived nonsense. It's not based on the physical reality. If you actually look at the real physical radius or diameters of the proton and neutron and electron, it doesn't match up. And why would it? I mean, why would we expect it? This is something that's been forced into there. There's no reason that we should expect protons and electrons to have the same angular momentum. They have different mass, different size. No one would expect that. It would be highly unusual for that to be the case. It would be a big surprise. And of course, the big surprise is you can shoehorn it in if you make yourself believe that the radius of the proton is half the proton's Compton wavelength, which it isn't. And so that's what's happened. Physicists developed this contrived idea before they knew what the true charge radius was. And then once they realized what the charge radius was, they didn't go back and fix the problem and realize the whole spin conservation law, the way it was applied, is nonsense. So this is one area where particle theory is nonsense. It's invalid physics, or fictitious physics, as I like to call it. And I'll talk a little bit more about that in a couple other videos, because to me this is, well, it's one of several big problems with the standard model of particle theory. One of the things that got physicists into trouble. And one thing that shows how physicists are blind to the facts. They pick and choose what facts they want to use and interpret, and they'll ignore the real physical radius of a proton because it doesn't match their ideal system where protons have the same spin as electrons. Well, I hope you enjoyed this video. I hope it wasn't too technical or mathematical, but it's important. And please share it with your physicist friends, and like and subscribe so you can see my coming videos. And also, if you'd like to read more about particles, you can buy my book, Go Buy Quarks, the Onium Theory. I discuss this in a little bit of detail. And also, my 100 Greatest Lies in Physics book has a lot of these sorts of problems, although I don't go into detail on this one in that book. And on my first book on the zero-point universe. And I'm a retired independent researcher, so when you buy one of my books, that helps me in my retirement, maybe buys me a sandwich, and so I appreciate that. And so, thanks for watching.